So thanks everybody for being here. Bert and I today are going to introduce JAX to you for scaling up artificial life. So we will split this talk in three parts. The first half an hour will be a crash course on JAX, and I will try to focus it on things that I think are worthwhile knowing to not have headaches in the future, or that are more specific to artificial life. After that, we will make things a bit more complex. We will go, Bert will present Lenia and also some, code base and framework that he's using for working on Lenia and Lenia-like systems. And with time, if time allows, I will also show some examples on what you can do with Biomaker CA using JAX. So some crash course on Biomaker CA and maybe simulating some new materials and visualizing them. So with that in mind, as I was saying before, for the people new here, we have, you can access the tutorial link from the A-Life conference website, and then you have a lot of collabs of what you're going to show. So you should be able to reproduce most of what we show. Okay, so let's start with JAX. For the parts on explaining JAX and for Biomaker CA, I will use Google Colabs. I wonder how many people are actually familiar with Google Colabs. Can you raise your hands? Okay, that's almost everybody. So I will be faster than expected. So if you're not familiar with Google Colabs anyway, they are essentially an online version of a Python notebooks that are very useful for reproducing things in the same way between different researchers. So it's very nice to use. And you can use different runtimes. In our case, we have Colab Pro Plus, but even with Colab, normal Colab, you have access to GPUs and CPUs, and I think TPUs. In JAX is something which is wonderful and can be executed seamlessly on CPU, GPU, or TPUs. But just to show you, the usual case of people when they use it is they would use GPUs because JAX is very good for accelerating programs. So you can write things and they can be executed on CPU, but that's a bit of a waste. You usually want to have an accelerator with that. So what you would usually do, you select a runtime and then you connect to it. And then you can just execute and you will have this, in this case, a GPU connected to your runtime. One of the things that you can check is also what is the GPU that you're connected to. One important thing is that then you would just do imports. So you import JAX and you can also check what devices JAX is using. So in this case, you will see that the devices used by JAX is CUDA. And that's as far as you need to know because everything else will be seamless. For this specific collab, I can show you something a little bit more if I use TPUs. So I will actually just change the runtime type and use TPUs, but everything works with GPUs. And so you don't have to worry about TPUs. It's just that with TPUs, we will have 8 parallel processes, which makes some interesting things. If you're wondering now, if I do NVIDIA SMI, there's no NVIDIA in there. But when you import, you will see much more devices. By the way, it takes longer to load the number of devices, I expect, because it's more distributed. So there's some issue with multiprocessing. So JAX is very, very similar to NumPy. How many of you know NumPy? Can you raise your hand? Awesome. Okay. But even if you don't, essentially you should think about it as a way to compute matrix multiplications or algebraic operations very, very quickly. So now you can see that the devices loaded by JAX are much more. They are all TPU devices. And I think the only constraint really is that you want to have all devices to be the same. You can have multiple GPUs, you can have multiple TPUs. As long as the devices are the same, it will work.
Also works for CPU.
Sorry?
CPU.
Also CPUs. Yeah, you can also have multiprocessing with CPU. So I will start by showing the similarities of JAX with the NumPy, and then also where they differ and why you should care about it. So some things are like literally the same. For example, if you want to create some arrays, it's exactly the same for JAX and NumPy. Do you see well? Do you want me to zoom more, by the way? Is it clear? Okay, perfect. But note that there's a difference here because the type in JAX is an actual array variant of JAX. So it's essentially works that it will be executed usually in your accelerator, so in your GPU in this case, or TPU, sorry, in this case. You can do the same also for like initializing arrays with a specific value. It's the same for NumPy and JAX, and you can sum them and everything is fine and works completely fine. Essentially, whatever you expect from NumPy, you will do in JAX NumPy. Here are a bunch of examples. You can initialize with ones. You can do scalar multiplication. You can do just array multiplication, vector multiplication, tensor multiplication, division. You can do the transpose. You can do matrix multiplication. You can do Einstein summation that whoever knows it's wonderful, and who doesn't know it thinks it's like a completely alien language. In this case, I'm literally doing this matrix multiplication with much more complex nomenclature, but it becomes very useful when you get more dimensions. So why do we care? Well, first of all, what are the unique parts about JAX, and what does it make it different from NumPy? So first of all, JAX is purely functional. So all the inputs will have to be immutable, so that you cannot just modify them and have an unexpected behavior. So there will be things that will be different from NumPy because of this reason. And we will like think of, by the way, like functional paradigms are beautiful for reproducibility because you are generally sure that if you execute something one time, the next time it will be the same, and you don't have to worry about anything which you're not passing directly. There are exceptions. I don't know if Alex is here. Alex knows exceptions with GPUs, very edge cases where GPUs are non-deterministic, but usually it's completely like reproducible exactly how you execute code. So in NumPy, you can just easily modify an array. For example, you start from zeros and you say, let's modify the first row. And first it's this, and then you just modify it like this, and it just works. Wonderful. If you try to do the same in JAX NumPy, it will not work. It will tell you that it does not support item assignment because it's immutable. It also tells you how to do it. So don't worry about it. Even if you just forget about it, it will be explained. You use this different thing that essentially says you want to modify at position 1, which is the same as before, this array. This works. And of course, though, this is not modifying the array. It's creating a new array B. So the previous array doesn't get modified. If you're curious, you can do much more than just set. You can do many other operations there, like add, multiply, and whatnot. Now, one of the coolest parts and also differences is randomness in JAX, because in NumPy, it's handled automatically. You don't even need to say what is the random seed. So if you use NumPy random and you say you want to create a random normal distribution for a certain mean and standard deviation, you run it twice and you will have 2 different values. That's not what we want. This is actually bad for reproducibility. What we want is to be able to control this much better. So although, I mean, okay, you are a seed. So like if you don't mess up, this still works, but there are many situations where you don't realize that you are not, that your code will have different behaviors. So to make sure that everything works better, instead, you use JAX random, which generates a key, just like you would use a seed in NumPy. But now you actually are responsible for passing a unique key every time you want to execute a random function. So if you want to do random here, random normal distribution, first of all, this is one of the very rare times where the API is different. You have to generate a standard deviation of mean 0 and standard deviation 1, sorry, a Gaussian with that. So you then just multiply standard deviation and add the mean. You have to do it yourself. But you can notice that if you reuse the same key, the result will be exactly the same. So what you instead do is you split the key. There's this operation that says split. And then the most like common way is you generate a key that gets sent here, then you split again and use again this newly generated key afterwards. So you pass this key name, because it's useful to do it like this, forward. You never use it effectively on any function, but you use a new key that you generate at the time. And when you do that, the results are different. Cool. Now, this is an annoyance. So why do we care so much? Okay, sure, reproducibility, but what are the superpowers? And the superpowers is essentially acceleration that comes for free and very easily on like when working with JAX, and also like it's even easier to write code, as we will see later. But let's start with acceleration. So say you want to compute a function many times. Like let's just say that I want to write this function for some reason. It's called geometric step function, and just says return me x plus 1/2 to the power of I. And I want to do it 1,000 times. I should have executed this before while starting to talk. So the way that we would do it normally, for example, even if it were in JAX, is that you do a geometric step, and then in this case, I add a log and you repeat it in terms of repetitions. Now, this is very inefficient. This is not how you should be using JAX. If you were to use NumPy, this would be extremely fast because it just does everything on the CPU. But here you are passing everything to the GPU many times, and you essentially have to figure out what to do every time because you're compiling the function many times. So this is extremely inefficient. It's not how you use JAX. By the way, the result is 2. It gets to 2 very quickly. And yeah, it's very nice. So completely useless to do this computation, but at least we know that it converges, so we don't have to worry about what it does. So it took 34 seconds. Okay, so the first superpower is to do just-in-time compilation. You just do JAX JIT of a function. This is thanks to Bert that made this nice drawing, so we will use them a few times. And it makes it super fast. What it empirically does in practice is this. So now I will show you this way to JIT, but there are two ways that you can compute JIT. The usual way is that you use a decorator that gets put into the function that you want to JIT. So this thing will be printed only during compilation. So even if you are calling this function many times, because this thing is something that didn't change, this will be printed only once during the compilation. And then the system will remember how to compile a function. It will just use the function directly. So this is instant now. And as you can see, this is printed only once. So even you can do whatever you want. This thing might take time to compile. The function can be as complex as you want. You can be a function that composes functions, and that's completely fine. There are some limitations that we will see about what you can put in there, but it will be compiled only once. Well, with some caveats that we will find out. So this is much faster, but this is also not the way that you should use JAX, because you're using a loop outside with Python logic, and Python logic is very slow. So what can we do to make it faster? Well, we can use the JAX way, or like the parallelizable way, or the compilable way to run loops. So there's this very scary thing which is called scan. You should think about it as a for loop, essentially. It essentially says you start with an initial value, and you will update this value many times, and then you return it at the end. That's the easy part. Another easy part is that you can pass an auxiliary input that tells you usually the index, for example. Tells you like the index of this loop is index 0, 1, 2, 3, and so on. And you can generate auxiliary outputs, which are this YS, which is one auxiliary output per execution. And when you do this, it will compile. So as I was saying before, when you do JIT, it will compile and then make everything fast. This automatically happens when you use a scan loop as well. So the functions that you use will be compiled. So the way that you would transform the thing before is that you got the geometric step. This time, the X I'm calling carry. In this case, it's literally the same, but the carry could be also like a tuple, a dictionary, whatever you want, as long as it's consistent from the input to the output. So you don't want to change the dimensionality of the output here when you return the carry. You do the exact same thing. This is, again, going to be printed only once during compilation. And you also return a carry. Sorry, you can return something auxiliary. Because I wanted to return the log to say the value of every single execution, I will return it as well as a result. And then you start with a certain input, which is the carry, in this case, starting from 0. I pass an array of number of repetition size. So this is a range. It's all values from 0 to 999 in this case. and this will execute 1,000 times. And this is extremely fast, but it was already faster, but it becomes much faster when you add some zeros here. So if you do this, it takes 1 second here in this example. And if you do it here, it will take essentially the same, because all the time that is taken there is for the first step of compilation. So when you compile the function the first time, it takes time, and then it's extremely fast. All right. But JIT, of course, has its own problems, because when you want to do just-in-time compilation, essentially, you are compiling a function, and the function will take some variables and output some constant values that you can think about variables, and output some other constant values, some values that are all immutable. Now, suppose that you wanted to have a function like this. It's a complex functions that essentially says you pass 2 inputs and an operation, and you want to say, let's just return the operation with A and B. Now, no, as I was saying, this is blasphemy, because this is not sliceful what I'm doing here, because I'm adding a global counter to tell you what is the compilation number. This is just for fun, to show you that they can count the number of compilations that happen. So in this case, this is not JITed, of course. So what it's doing is, when you run a function like this, you will compile it twice, or execute it twice, essentially. One for the operation, which is sum, and one for the operation, which is subtraction. Now, if you try to JIT it, it will not work. This is because it's not written in a way that is friendly to being automatically compiled. So in this case, it tells you the value of function is not an abstract array. So everything which is a variable, it needs to be an array, or at least interpretable as an array. So scalar values are fine. It will be interpreted as arrays of size 0. So the way you do this is you do JIT again, but you say that some of the inputs are actually static. So note that here I'm using a different way to JIT, because not too many people are familiar with decorators in Python, but if you write the @JIT, or you write jax.jit and you pass the function, it's the same. So in this case, I'm showing you a different way to do it. You take a function and you do JIT, and then you pass this extra auxiliary input, which says, what are the static argument names? So here I'm saying the operation 1, the operation is a static value. So when you execute it like this, suppose that you want to use the same operation many times, like for example, addition. Then it will compile only once, and it will not recompile every time that you reuse the exact same function. But whenever you want to use a different function, the function gets recompiled. Think about it like it has to map to the GPU a set of operations. And if you pass something which is a static input, which then it will have to recompile to figure out what to do. So you generally do not want to recompile often or ever. Like you want to compile once usually when you use JAX. So this is the alternative of how you could do it. So you can say JAX.JIT, and you can do partial static art names. This is what people usually do. It's exactly the same. This @decorator essentially is taking the function as an input to process it, and partial is telling you that you didn't complete the function, and then you will use it later. In this case, when you complete it like this. So this is the same. And I'm not putting the compilation time here. Yes. You mean here? Like if, for example, if I were here and like this one? Yes, it should recompile as far as I understand. So we can show you. Oh, no, it didn't. Okay, sometimes it does. The thing is that it saves in memory as much as it can. Sometimes it will not recompile, but when you get bigger and bigger functions, it might. So don't rely on it not recompiling, especially when you get a lot of operations. But yeah, okay. So for small ones, it doesn't. Okay, so conditionals, of course, are another issue. Because so if you want to do a conditional like this, of course, this is the way that you will write it in Python. As opposed to say the operation, you say if the input is add, then you add, otherwise you subtract. This will work without JITting, of course, And you can do static arg names as well, like I showed before. So the same thing that I showed you before would work. But you are actually compiling, you're using two different functions and you might have to recompile many times. Later, I will show you how you actually handle this dynamically in the JAX way. But you can still do static arg names like this with conditionals. So this is not something that JAX understands when it executes. It understands it when it compiles. That's the most important part. So you can use if to compile things depending on your input, but then these conditionals have to be static inputs. Right. Now, the biggest superpower of JAX, in my opinion, is vectorizing. It's the most amazing thing. And the best reason to use JAX and to get excited about it is that makes writing scalable code trivial. So this picture should explain it quite well. You start with a function that has one-dimensional or zero-dimensional inputs to zero-dimensional outputs. And then you do JAX VMAP. And now it works from one to one, becomes many to many. So it just does it in parallel. And this is so nice to work with. So this is like, let's start with some basics here. Suppose that you got a function which is just matrix multiplication. So in this case, you look at the shape and it's something which has the final output shape is 2 times 4. What if you wanted to perform this operation with an extra batch size? Well, in general, although keep in mind that specifically for matrix multiplication, this thing is intelligent enough, it would do it itself. But in general, what you would do is that you can just say JAX VMAP and pass a batch of inputs, in this case, a batch of input x's and a batch of input weights. And it will just naturally work. So you don't have to worry about anything. You just think about the low level, and then you just say VMAP it, and it will work with a higher number of dimensions. And you can do it for everything. You can do it for matrix multiplication, but you can do it also for like executing a cell and then wanting to scale to a grid, or you can say I run one simulation and then I want to run n simulations. Also, you usually don't do what I said here, because usually you want to have one weight matrix and multiple inputs. So the way you would do this is you say, again, you use the beautiful partial function to say, the function f will always get as input a specific weight matrix, and then I will pass a batch of inputs when I VMAP this function. So in this way, the output is the same as the one before, but you are not passing a batch of weight matrices. You are only passing one weight matrix once, which is what you usually want to do. So as I was saying, this is wonderful. So I do it all the time. You want to create a cell in a 2D grid to perform an operation. So you say the function of the cell depends on the neighborhood. And you just say, well, I locally think about what to do and just execute it. And this is the output. Then you VMAP it twice. Now it works on a grid, which is amazing. You don't have to worry about anything else. Now, as I was telling you, for fitness functions, you can think about making a simulation. So you say, you have a function that says you want to simulate an environment and then evaluate it. So you would want it to be random because it depends on something that could be as complex as you want. As long as it is jittable, you can do whatever you want there. And then you want to return a fitness. So for example, suppose that this is the environment and you could do a simulation like this. This is all jittable. So this is jitted. And you get a value. Now, if you want to run it 10,000 times, of course, you can do a for loop, which is something you should not do. And it will eventually work. I don't know if I just shoot myself here. Okay, 4 seconds. Or, as I was saying before, you can VMAP it. In this case, you can say that I'm passing the environment as a constant and I'm passing 10,000 different values for the keys, but you can also pass different environments every time. Question? E is a variable, so it's completely fine. It's like an array that gets interpreted as something which like doesn't need to be recompiled when you pass a different key. But again, the dimensionality of the key has to be the same. Yeah, another question? Yes, strings are not arrays, so they have to be static as inputs. Yeah, so if you pass strings, and the arrays are not static. they are not immutable. But if you were to transform it into a tuple, tuples would be valuable inputs if everything that they contain is a variable that is like, for example, JAX convertible. You can pass dictionaries and it's completely fine as well. So, I mean, that's because it gets converted into a static dictionary. So usually I have to check with lists as well, because I think that JAX is smart. Whenever it can convert the input to something static, it will interpret it as static. And then if you don't pass a different dimension next time you pass it, it will work without having to recompile. So yeah, I was saying this is just very fast, but for interest of time, I'll go faster. You can do the same with PMAP, which is just parallelizing across devices. So if you get multiple devices, like in my case, I'm using a TPU, you have 8 devices, you can do PMAP. There are very many caveats here. So if you ever want to use parallel processing, read the documentation. One important thing is that you cannot do PMAP for more than the number of devices available. So if I have 8 devices, the maximum size of the leading axis has to be 8. Otherwise, it will not work. And yeah, here I just prove it. You can do local count, device count to know how many devices you have. And if you do something with PMAP with the size being 8, it will work. But if you do it with the size, which is 8 plus 1, it will tell you you can't. I don't have time for the extra, but the most important part, if you care about PMAPs, is that by now researchers use sharding, and JAX automatically takes care of figuring out the most efficient computation. So it takes time to understand sharding, but it's much better in the longer term. And the intuitive way I should think about it is that you have some inputs which tell you how to allocate resources based on what you have. So you pass some arrays that knows that a certain part will be executed into a certain device, and another part will be executed into another device, and it's much easier to think about it when you scale. Now, conditionals. So suppose that we want to do something like this, that we want to have a function that executes the square if it's greater than 0, otherwise it's 0. It cannot be jittered because, as I told you, the conditionals are not something that are valid ways to use JAX, but you can use JAX/cond. It's just a different way. And the way that you can execute it is like this. It tells you this is the condition. If it is true, I pass X as an input, and the functions for the truth value, for the true value is the square, and the output value is 0. Now, there is a caveat here. You need to have the same dimension on the output of those functions. And if that's the case, it will work. Also, this is sounds like it's going to be efficient, but it will not be efficient almost always. Because what it does, it will execute both branches whenever you use a VMAP. So if you don't use a VMAP, it will actually execute only one branch. But in complex code bases, you will almost always use a VMAP eventually. So you should assume that if you're using a JAX/cond, you will execute both branches, and then it will be just masked. Yeah, so here, yes. So for conditions, so they're asking to repeat the caveat. So in theory, you would think that when you use a JAX/condition, you will only execute the branch of the truth value, where the truth value is. So for example, if it's f of 2, we'll execute only this. However, this is true only when you don't use a VMAP eventually, a VMAP eventually with this function. So if I were to say VMAP of f, like here, this will actually execute all branches. It will be very nice to work with it anyway, because you don't have to worry about anything, but it will be more wasteful. You will actually execute both branches. Yes, question? Yes. So you need to be careful, or you need to do different approaches for handling, conditionals in a very efficient way. Like in the BioMaker CA, sometimes I do care about this, sometimes I don't. And when I don't, it's very wasteful. So maybe we will see some examples later. But yes, whenever you want to essentially do a condition, GPUs are smarter than that. This is something that is done with JAX. If you have some implementation with CUDA, they usually are smarter and they just return early, for example, and they can have much faster executions. So this is one of the limitations of JAX. Question? So the question is, what happens if there's dividing by zero in one of the branches? I think, yes, it will be bad because you will probably be masked. So I didn't check this explicitly, but what I'm expecting that would happen is that when you do VMAP, it will essentially sum of the outputs. One is masked by zero, but if you get none, you don't know the behavior, it will propagate a none.
The other by zeros will become NAN.
Yes, but yeah, but even if it's in a branch which you're not executing, it might be. We have to check. Although I think I do it. So maybe they are smart and they don't make it happen. Sorry?
If you are asking for a particular condition, then it will be a problem with this return at the end. But if you are going for the other condition, you return it.
Yeah. But when you beam up, you execute together. So I actually think I tested it. It shouldn't return none. So they were smart and maybe do a none check before do something there. Thankfully. Okay, I don't have time for this, unfortunately, but this. So this is like I promised. Yeah, I promised to explain how you would use this ISAD situation here. So if you actually want to pass a function, you could do something like or a conditional. Well, in this case, a conditional, sorry. You say is ISAD, then do plus, otherwise minus. Note that you don't even need to pass any input. These functions are lambdas. We don't accept anything. It just works. So this is the way you would do it, and it compiles only once. And as you can see, it just compiles once. So this is the proper way to do it in these simple cases. So there are other things to keep in mind on dynamic arrays. Usually, everything works fine. So suppose you get this array, size 10, and I want to do something relatively complex. So here I'm saying at position 3 to 5, set -1, and this is jittered, it will just work. That's completely fine. What will not work is if the index to start is index to start. If the, this is wrong, if the dimension, well, no, actually, no, if the index to start is dynamic, yes. Because what they want is to make sure that you are always updating with the same fixed size, because you want to compile into a GPU. So they want to make sure that if you want to update something, it has to have the dimension, in this case, always of size 2. So this is not allowed, but you can do the same, just with a different nomenclature. And they tell you. So you try it, it will not work, and it will tell you somewhere, use dynamic update slice. So you just do this. And now it becomes clear that you are pretty much forced to have a fixed size, because here it tells you this is the array to update. This is the position. Note that this is a tuple of positions, because it tells you for each dimension what is the initial position. And this is the array. It is not, it literally tells you this is the fixed array of updates. So in this case, there are 2 updates that tell you of value -1. And note that weird stuff happens when you do not take care of where you're updating. If you are at position 8, everything is fine. Position 9, that's wrong. Position 10, that's wrong. This is your responsibility to make sure that you don't go out of index. Otherwise, the behavior is undefined. Now, of course, you can do it also with multiple dimensions. So you can pass 2 indexes and an array which is multidimensional, and it just works. But again, take care of what are the indexes and the sizes yourself. The last thing that I want to show, I think is last, but very quickly, is grad. So gradient is another superpower of JAX, which is not as relevant to many people in the ALF community, but to some people it is. And it's just that it's very annoying to have to do automatic differentiation. So whenever you get a library that does automatic differentiation, we are happy. JAX is a functional automatic differentiation. So you create a function as complex as you want, and then you say, let's generate the gradient of this function, so that it generates you this function below, and it magically works. So whenever the JAX functions are valid, then you can just do grad. And it doesn't matter how complex they are. You can also do value and grad together, which is usually useful and cheaper to compute. So it returns you both the value and the gradient. and I don't think we have time to explore this. But there's in the collab that is shared on the tutorial, I show many different things which are of higher complexity. But I think the only important thing to notice here is that it computes gradients only for the first input. So what you usually do is something like you get a function, and the first input is all the parameters, and you compute gradients only for those parameters. So what happens if you want to have a very complex neural network and you want to compute a gradient there? You pass a dictionary usually as the input, or to a tuple, and then they will take care of it. And you compute gradients for the entire tree that you pass in the first value, but only the first value is the one that will have the gradient computed. And that's it. The last thing that I want to show is that I put some extra links here. There are some examples on how to execute train micro NCA in JAX. There's a very cool way of doing recasting with JAX. So just showing, yes. The results will be something as this, and it's all executed with JAX. So it will become your 3D rendering engine, just executing everything in JAX, and it's very fast to do. Code bases and very useful libraries for what I think might be relevant to you. If you want to use inferentiable JAX, you should check Flux, HiQ, and Optax. If you care about particle simulations of any kind, JAX-MD is very cool. Makes it easier to think about many problems. And evolutionary strategies, EvoJAX and EvoSAX, but Bert will show you something about it. All right, so let's move to Bert now. So I'll stop presenting. Stop sharing. Do you want this?
Oh, yeah. Thanks. Yeah, thank you for Ettore for have a quick tutorial about what are the superpowers and how to use JAX. Like you need a pure function to pass into just JIT or Remap or PMAP to use the superpower. Okay. Yeah, presenting. So yeah, this is a tutorial about the JAX, and I will use linear as an example of how to use JAX to speed up or scale up artificial life, because at some point I was using some website to do the experiments, but after using JAX, it's much faster. Especially I've just used JIT to JIT my function. It will be like many times faster. First, I will show that using a library called EvoJAX, which was developed in Google Brain before, but now Google DeepMind, is a library for using evolutionary algorithms. So I tried to change I already have a code that implement linear inside JAX, which just JIT is enough. And then I use that code, modify a bit, and then plug into the EvoJAX framework. So this is just a normal linear. Okay, not showing this one. But then I change my coding. This one. So this is a notebook that I try to use EvoJAX to evolve the fastest moving linear creature using evolution algorithm, which is specifically is a CMAES. And then I won't run this collaborable now, but we first have some definitions, settings, and load some patterns here, like the pattern I'm using will be a pretty complex one with 3 channels. So you can see red, blue, and green. First I will load the pattern into the system. What I'm doing was I have some hyperparameters. For example, the size of the kernel and also the initial parameters. Lots of calculation. I will calculate the kernel. If you calculate the kernel and things like that, and also prepare for some FFT of the kernel, which is just to utilize a faster calculation later. But the core here is to calculate, to make a carry object. The carry objects is actually a collection of all the materials I will need during the evolution algorithm or during the simulation, which use JAX to make it faster. So I will put all the material like the array itself, which is A, and also the kernel, the parameters, hyperparameters into one carry object. And also because the JAX system, it will need a certain kind of gene, which is just a single array of numbers. So I also make this gene, initial gene, which is a concatenation of parameters and also the initial condition, initial cells. So loaded with this aquarium pattern, which looks like this. This is one aquarium creature. And while I was making a carry object, because I want to use JAX-scan function which is actually a for loop inside JAX. Inside JAX, we don't use for loop or if then else. We have to use these specific constructions. For if then else, we will use JAX-cont, which is a conditional function. And for loop, we will use a JAX-scan, which will input a initial carry, which is all the materials we needed. And then it will keep looping for like 100 times. And then we will output the last version of the carry. And for XS and YS is usually is not used. We usually just use the carry to get all the outputs.
You also have the for I loop or while loop inside JAX. Is it like faster than scan, or is it based on scan?
Sorry, can
you have like a JAX dot for I as well. Is it just based on scan itself?
Yeah.
Or is it...
Sorry, you can repeat it because I don't hear it.
Is it based the for loop based on JAX scan? Which for loop you mean? Sorry. For I know, yeah. I think it's the similar thing. Yeah, it's the same thing actually. It's the same thing. Yeah, just different names. Yeah.
While loop is not the same. It's not differentiable unless they fixed it eventually. So while loop is different.
While loop.
While loop is different.
While loop. Yeah.
Scan loop is the best, so that you are sure that everything works.
Yeah, while loop for loop is I use just like scan because it's the best version. Yeah.
You are not presenting.
Oh.
You can ask a question.
Okay. Like they say, you can ask the number.
So the question was, if you want to have a variable number of in scan, can you do it? The answer is for no, because you are compiling a fixed size explicitly. So yeah, it is a limitation. It's weird. But actually, I have to check. But I think so. You can compile the function once and then use it with different values. But yeah, I have to check actually. Maybe yes, but would be weird.
So I'll continue. So if we have a gene which is a array of numbers, and then I will need a function to express that string into a carry object for the simulation of the evolution. So I have a function of expense gene into carry, and then the step function, which will carry out the simulation, one step of simulation, which is just apply the linear mechanism, the algorithm, into the function array, and also do some convolution, and then we create a carry object pass through the scan function, just that scan function. So also I'll need a fitness function for evaluating for the evolution algorithm. So here it's more flexible. You can just go for a higher speed, higher angular speed, or more mass variation, something like that. So here I just I want a higher average speed, and this will be the fitness function. You can notice that I don't have the JIT here, because JIT, the thing about JIT is, if you have JIT, the most high level function, if you actually during compilation, it will go through all the subfunctions, and in case all the subfunctions are JITable, then it will like compile all the subfunctions during the compilation. So for this subfunction, I don't need to JIT it now. Yeah. And also the same for the simulation and evaluation function. But here, simulation, I will use scan here, which will initialize with initial carry, and then we'll do it a number of steps, and then it will output the final carry. And also, actually, I can specify which type of data I want it to output, so that I can show it to the screen or for another analysis later. Yeah. And then I will calculate the last fitness of this simulation. Sorry? Oh, yeah.
No, so you don't need to JIT anything besides the last function. So it will just JIT compile every other function inside the other function. So it's actually best not to do JIT inside other functions, because then the compiler cannot optimize it at best. So you ideally want to say JIT only the last layer, completely last one. You can do it, but it's not needed, and sometimes it's worse.
Yeah, or if you cheat the subfunctions, maybe you want to use the subfunctions in the other side, like not only used by the main function. So cheat the subfunction, you can run it like a million times. It's okay. But if you cheat the main function, it will compile all the things again. Like.
But then this function has an if statement. Is that?
So the question is, this function we are seeing as if statement, is it not JITable?
Is it JITable? Even if you see that if then else here, usually we don't use if then else inside a JIT function, but here, because I only define the fitness function once, so actually the if then else is only run once. I decide to use average speed, so it's actually when you're JITting compiler function, it will already fix the using this
No, you're even passing metric as a variable, but it's still fine because you're not passing it as a variable at the higher level. So if you have internal functions that you want to pass variables just to compile it differently, that's fine. It's just at the highest level that you need to think about static arc numbers.
Yeah. So this is the initial creature that is quite slow. And then I will run the eval JAX, which is also written in JAX. So it's just declare the solver, which is a CMAES. And then use the eval JAX architecture, just ask and tell architecture. And for loop, I will use ask the solver like what are the best gene for now. And then I will use the evaluation function to calculate the fitness function for the batch of genes, which is a bunch of simulations, and then calculate the fitness function. And then I would tell the solver the fitness of each of the genes. And then the CMAES solver will do all the heavy stuff for me. And then for like 30 iterations, this is the curve of progress. The fitness function goes up, yeah, because it's faster. Yeah. And this is the fastest creature, at least for this round. It's the result of the CMAES method. So this is one usage of. I also want to highlight one thing. When we are evaluating the fitness function, because the eval JAX, it will output multiple genes for us to evaluate, like 10 or 20, it depends on how many we want. We can use VMAP to apply on the evaluation function. Evaluation, here, it will just run like 100 time steps simulation for one gene. But if I use VMAP, it will like parallelize the whole function for me for free. It will evaluate all the genes at once. Of course, it will, if you have multiple GPUs and using PMAP instead, it will distribute into multiple GPUs or TPUs.
And we will also compile it. So he's using evaluate and doesn't need to do JIT there. So it will compile only once because he did this VMAP here.
Yeah, VMAP and PMAP, they will JIT for us. So this is linear in eval JAX. Last year in Gecko, I also presented a large-scale linear simulation using JAX. So this is the large-scale simulation. This is real time. So you can have a large world, and with starting with a few self-replicating creatures, and then it start to evolve. The evolution here, I say, is an intrinsic evolution because the fitness function, we don't even have a fitness function here because it's just for survival of the patterns. So at the last, the survival pattern is like this kind of linear type of sweeping or the space. They are the winner of the intrinsic evolution. So I will talk a bit about the work in progress, which is a linear engine. I try to write a library, which is based on JAX. But because linear, we now have many variants, like asymptotic linear, particle linear, flow linear, and also some of my secrets developing versions of linear. So I will write a library so everybody can just code easily. So the library will consist of a few nodes, which is really like a layer of neural networks. So in a neural network, we have convolution layer or dense layers. Here we will have a convolution node or growth node or flow node. I will explain a bit later. Do you have a time? Okay. And then the model, we have different models like asymptotic linear, liquid linear, particle linear. And also we have a few UIs to choose, like Jupyter Notebook or Test Prompt or window. The basic architecture is we have a
Let me refresh in the sharing. Just stop sharing and share again.
okay. Mhm.
You see the whole screen?
Oh, yeah.
They're not screen, they're not sharing.
Let me try again. Entire screen share.
Okay.
Yes. Okay. So this is the architecture of a node, which is like a neural network layer. The main thing is the apply function here, which is pure function that apply the logic, and then it should be able to be jittered. And others are just some initialization function, and also the green patches are data, like more like arrays inside data text. So the overall architecture is we have a dictionary of data pass through the main logic of the node and then have an output data. So an example node is a convolution. You just have some preparation like refresh. Refresh means just to calculate the kernel, but you don't need to calculate the kernel very often. But the main thing is the apply function, which just to apply a JAX SciPy signal convolve to convolute the array with a pre-calculated kernel. Yeah. So this is one example of node. A model is just a combination of data and a network of nodes. So a network of nodes is you pass through different logics and inside a step function. So for example, this is the original linear model, and we have a linear dot model dot linear. This is a bit complicated, but it is a flow chart of the applying the internal structure of the model, and this is the pseudocode of the using the library. So here is the, I'm using the test prompt UI to show this simulation. Yeah, so I was just showing the linear model, and then I can change to another model, just random. Yeah, load the linear model and then just random the world. And then I have a UI, which just a for loop to run the model and then display the array. Yeah. Let's save it and then I run it again. Yeah, just random initialization. And then the good thing about this architecture, this library is I can change the node. For example, actually, if I initialize a linear model, it will use FFT, the fast Fourier transform, which is faster. But you can define your own node. For example, I want to use the slower original naive convolution. I can create a new node, which is convolve naive, and then assign to the kernel node. And then it's actually slower because the naive convolution is slower. But you can define your own node. And I'll show the flow linear here. Yeah, not very clear because it's using this test prompt. I can try to use the window version, window UI. Oops. Oh, I haven't installed OpenCV for this. Yeah, okay. And then I'll try to, this is the secret sauce, like we call it liquid linear, which is a continuous version of particle linear. Yeah. Also, you see some self-organizing pattern going on, but not very clear. Yeah, you see some kind of a cartwheel kind of pattern. So different kind of UIs, window, prompt, or Jupyter notebook. And also the data type inside, you can also define the data as integer. So go back to something called integer linear, which is a discrete version of linear. Even it's designed for continuous cell automata, but you can change the data type or even the number of dimensions. Like we can use have a 1D or 3D, 4D linear, flow linear. And also because the architecture, if we, for example, if you compare the original linear with flow linear, it seems the system is quite different and the pattern generated is quite different because they have different physics. We have mass conservation inside flow linear. The mathematical formula is a bit different. But if you go into the code level, if you use the library, it's actually changing a few lines. Oops, again.
Is the code which produces the rendering in the UI also repacked in Jitter in JAX?
Sorry?
The code that produces the rendering motion inside the UI
Mhm.
the video, is that also remapped in Jitter, or that's like, because I've tried using that on matplotlib, it does not work.
Oh, you mean output the integers?
Yeah.
They out in the view.
Yeah, on the video. Yes, it's
Oh, it's not integer, it's floating point. It's integer because you have to display.
If it's JIT, if you can JIT the generation of the video.
Oh, okay. Yes, when true that even the UI, when you're making some videos, the generation can also the function can also be jittered. Yeah.
So you can JIT like the generation of all the frames essentially, because you can do it essentially using JAX NumPy, but eventually you have to pass outside of JIT to visualize it.
that part.
No, that part cannot be JIT.
Usually you when you want to output, you pre-calculate all the information first because the matplotlib cannot be jittered. So you produce all the frames first using a jitter function, and then you push it into a movie. It'll be faster. So for full linear is just change the very last part of the algorithm just by swapping the node, and then it will do the work. Particle linear is also you have a jitter function inside, which is a calculated field function, and then use some gradient. Yeah, here use just the grad here, because actually the particle linear we will calculate the gradient and follow the gradients to the lowest energy, things like that. Also grad and Vmap. With just is pretty straightforward to apply these functions. Liquid linear. Yeah, so my part is okay. And Ettore will talk about BioMaker CA.
If you have any questions about the linear, just ask them now, will be a good time. You can hold this.
Not so much about JAX, but linear, like
Yes.
take a lot of weight. So that final dynamics, how does that compare to random initialization? Similar or just something different?
You talk about the initial condition. Is it random initialization better, or starting with some existing creature is better?
Yeah.
It depends on what you want to achieve. Like I usually start from some existing pattern, like the OBM or some self-replicating creatures. Maybe easier for my experiments. But if you want to study the overall mechanics or overall some global behavior of the parameters of the hyperparameters, then I would say a random initialization will be better for your experiments.
All right, you can hold this. You can mute if you're not using it. So for the remaining time, let's see how far we can go with the BioMaker CA. Maybe we'll get to the point where we can implement new materials. Otherwise, I will leave the references for seeing how it's done. How many people know what BioMaker CA is? Can you raise your hands? All right, there are people that don't know, so let me just show you one video to explain what it is about. Literally one video because we don't have time. So BioMaker CA is a biome simulator. So it generates a biome of plants that tries to survive and compete for resources. All of this is implemented with cellular automata. So the rules of all the materials are with cellular automata, and the rules of the agents are implemented with neural cellular automata. There's a lot that can be done here. We will focus only on very few things to show some examples. The code base is quite convoluted, but modifying it is relatively easy. Plants fight for resources. This is relevant for what we will show today if we have time. The resources are generated from the top. There's some sun cells that generate nutrients for air, and from the bottom there are some immovable cells that generate nutrients for the earth. But we don't like the second one, so we will remove it and we will try to generate water that does that for us. So let's get some basics. So first of all, this is quite important. So the environment is everything has to be essentially some fixed sizes, because we have everything which is jittered and can be mapped however we want. So we will have an environment that you can think about as essentially, well, let's say a 2D grid where each value actually has each grid element has a lot of information. One of them is the agent ID, which is just a pointer of an index that tells you how to reference a certain agent ID. So we are talking about visualizing. This is perfect. So there's much more complex ways, like examples for how to visualize stuff. For example, the raycasting in JAX. But if you really want to go to the simplest possible thing, you can think about this concept that just takes an image from the environment. So I think this is useful for putting things together. So you have the function grab image from the environment, and you JIT it. You do it partially, though, and you say essentially the static arg names, so things that if they change, you need to recompile it, are the configuration of the environment and whether you want to color the plants by ID. So the simplest thing, which is not the actual function, would be something like saying, define a function that just maps one cell to a color. And you do it by saying, let's get the cell type that I pass as an input, and just map it to whatever dictionary. So it's just a dictionary that I have and tells me for this input index, output an RGB value. So you do that for one cell, and then you do vmap2, which is my implementation of vmap of vmap. So it's just a shortcut. And you pass then a 2D grid. You pass a 2D type grid and a 2D state grid, but for this specific case, you're only caring about the cell type. So it would be a 2D grid of indexes, and that's enough. We don't have time to actually go for more complex examples, but essentially the implementation that I have for making colors such as the one you see on the right is that you think about it only for the cell level, but you can add more complex things like saying, if I'm a material like air, I want to change the gradient of the color based on whether there's air or nutrients or not in there, so it becomes darker, and other things for the color of the plants as well. This is the step. It's very, very terrifying. So you have a gigantic function that executes one step of everything. It includes the logic of the environment, the physics, the material, execution the material operations, executing agent operation. The only thing that I want to show here is that you do a partial JIT, so you don't even have to think about passing all those inputs many times, because you will only do this partial compilation once, and then you will only care about passing 3 variables, which is key, environment, and programs, which will change every single time. The highlights are, let's say that this is the inefficient version, is that all material operations are executed for the entire grid. And then I must admit the material is wrong. This is because essentially I would have to use the JAX cond. So right now, unless I did something smarter, there would be no way to avoid it. So because material execution is quite cheap, I would say, for example, execute, imagine if everything were air, what would the air cells do? Imagine if everything were earth, what do earth cells do? And then I mask it based on whether you are air or earth or not. Agents, though, are way too expensive, because usually you can have like 10,000 parameters, relatively deeper networks. So for that, I actually use a budget. You just say only up to this number of agent cells are computed, and then I scatter them into the environment to update. I personally do that. I make sure that they are never above the budget, but you could also think about saying, if you have a much lower budget and only a random chance, like cells have a random chance of executing if there are many cells, if you want to make it faster. Something which is relevant for what we will try to implement. So think about when a cell of every kind, either an agent or earth cell, wants to act on the environment. There could be conflicts there, because say that you want to fall, like an earth cell wants to fall to the side, but another earth cell wants to do the same. You cannot allow that. So my solution there is you create atomic operations that can be either executed or just not executed. So you just say everybody proposes the action, and then we select a relative, like as large as possible, not optimized subset of operations which are not conflicting. The code is very complex, but it's JITable, entirely JITable. So this is to show you how the update interface looks like. This is the low-level interface that I will show you. When you want to update, you want to say you want to update a target, and how you update yourself if the update happens. Because, for example, suppose you're Earth, if I move to a certain position, I need to say that the current position gets modified. So I would have to say, how does my neighbor change and how do I change? So those are the things that would happen. And then if it gets executed, I execute both of them. So you have a mask that tells you whether something is happening, the type of update, the state, and the ID of the agent if it's an agent operation. Now, because this is at very low level, actually, this is done for multiplied by 9 in dimensionality. Because you could think that I can only just say, give me the index of the update where I want to update this operation. But because eventually you have to extend it to do essentially a scatter sum, I'm just doing it here. So I'm saying you have a 3x3 neighborhood, which is 9 different positions. So am I updating on which neighbor? So the responsibility for updating a cell in an exclusive way would be to say, I'm acting on neighbor 2, and on neighbor 2, I'm telling you that this is the thing that is going to happen. And I also say how I would modify myself if this happens. Okay, so before getting to implementing new stuff, let's see how we can implement how the things that we already implemented look like. So the first is air. Very, 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 very simple. So air cells always take, this is an interface. So the input is always a key, which is if you want to have a random behavior. Your perceived data, think about like 3x3 neighborhood, and configs that you just think about when you compile, you want to know maybe some parameters of the universe. And then you output an exclusive operation. And air, the only thing it does, it spreads through neighboring void cells. So there's this thing that sometimes a cell dies in some ways and it becomes void. So the only thing we want from air is that if there's void nearby, it will eventually become air. I don't even want to make it more efficient. I just say eventually become air. So the way you would do that is, well, just look for a random neighbor. So I say, random choice of these 8 values. Note that there's not number 4 here because 4 is myself, and I know that I'm not void, so there's no point in doing that. And I want to act on a neighbor. So I get a random index and I say, is the type of this neighbor void? This is completely fine because it's done with mathematical operations. There's no conditionals. I'm not using an if-else. As long as I'm not using if-else, this is compilable, essentially. So I create a masking, which is if it's void. And then you need to return this exclusive operation in this format. So for these cases, you're not even updating yourself. So that the actor mask, this part here, is all zeros. You're not going to change anything. In the target mask, I'm saying, I want to update a position random index if this void is true. So if I found a neighbor which is void, then I want to update. And the only thing that I need to update is the type. I want the type to be air. And I say, put at this position the type of air. And in this case, I'm saying that the state is 0 and the agent ID is 0, like it's set all to 0. So this seems like I'm saying this is the default and not changing it. No, I'm saying I'm setting it to 0. Because if you want to not change the position of the, like for example, the state of what you're acting, you have to copy the state from for that position. Okay, so that was easy. Now, Earth. Earth is the typical falling sand algorithm. How many people know falling sand games? Raise of hands. Okay, so falling sand games are usually cellular automaton-based environments where you just create some local rules for materials and you make them do stuff. And the very first thing that everybody does is you create heaps of sand. And the algorithm is something that says, if you can fall to the side, fall to the side. That's what they do. Here, because I hate myself, I created gravity. So gravity already exists. You can just say if a cell is subject to gravity. But maybe stupidly, I didn't make gravity a falling sand algorithm. I said it just fall down. So if you want to make it become a falling sand algorithm, you have to do something different. You have to say this. First, if you can fall below, do nothing. Gravity will take care of it. You just say do nothing and then it will fall. If you cannot fall below, but you can fall sideways, what do? Do you think you go down to the left or to the left? Okay, I guess it's difficult to interrupt. To the left, because then gravity will make me fall to the left. So this specific implementation needs that both the left and down left have to be free, because then the cell will move to the left and fall to gravity. Likewise to the right. So let's see how I do it. First of all, because it's easy, just start with all the final outputs set to 0 and modify them based on whether something happens. So the first thing I say is, can you fall down? And falling down is easy. You just say, well, ignore even the out of bounds part, because this is probably even not necessary. You can say, if the position below me, which is position 7, because it's like from 0 to 8 in the 3x3 neighborhood, is below me an intangible material. This is just an array. It's an array with indexes, and intangible materials are air and void. So one of those two. You could do also out of bounds and get rid of it. So I'm sorry that I didn't do it, honestly. If you can fall, then literally do nothing. Just remember you are done. So if you are done, this will be the mask that says don't do anything below. Now, if you are not done, you want to check if you can fall to a random side. So just like before, you take a random choice between left and right, and you check on one of those two positions. You could think about doing for both, but why not? Like, it's fine. Like the algorithm, like you just wait one more step or 2 more steps, and eventually it will fall to the side. So it's just slower. So you get side and downside index, and you do the same argument as before. Can you fall to that side? And the way you should think about it is essentially saying, is to the side and down to the side intangible? If the answer is yes, then you get this thing. Now note that the way that I did it was saying, I'm not done, and this is true. Because if I'm true, I already don't do anything and everything is masked. And now because I like engineering, I created a conditional update function that makes it easier to think about. And it just said essentially, do an update on the mask in this position with this value, if this is true. And you do it for everything. So in this case, as I was saying before, I actually update myself as well, because I need to move. If I need to move, I need to say, modify myself too. So in this case, the mask of updating is true for both the target and myself. And the type is, well, in this case, it's pretty simple. You modify the type of the target with your own type. In this case, it's cell. So you say, put my own type in there and put my own state in there. And in my position, I put my neighbor. So I do a swap. And this is the same for the state. I also do it for the update ID in case one of them would have an ID. Right now, it wouldn't make any sense because air cells and void cells don't have an agent ID. But if you want to implement it and make intangible cells which are agents, then this would make sense. All right, actually, we do have time for the fun part. So let's implement some new materials. So we want to, first of all, disable nutrient generation from immutable materials because that's weird. And we want to create water that it falls, touches the earth, and it gives it earth nutrients. And to do that, instead of putting water ourselves, we'll create a water generator material that stays in on the top and sometimes make water spawn. All of this is this is a spoiler. All of this is in the links. What you would do is create a copy. I have it here so that I already pre-computed some videos. So just connect to a GPU. Don't try this with a CPU. It will not end well for you. But any GPU is fine. It's just a matter of how long you have to wait. So once you're connected, the first thing you have to do is you install our package. So it's like from Git, from Git hub. And while we go on, so this is just imports. Those imports are specifically added for creating new types. Otherwise, you would require fewer imports. And this is the core of it. So hopefully it will look easy to you. It looked easy to me. I did it like in half an hour and then played with it for another half an hour. So half an hour, maybe like 10 minutes, and that's making sure that everything worked as I wanted was half an hour. So it's I try to make it as easy as possible. First, let's define a new name for the new materials. These names will be converted to enums afterwards. So you just think about the name, and then the system will use it as a way to map to an enum. So you say, let's use all of the original default materials, but add the water and water generator. When you do that, you need to add two things. The color, because we always want to visualize something. So what are the colors of those materials? And you do it by updating a dictionary, essentially. This is just create a new dictionary with this new dictionary, which is water and water generator key value pairs. You also have to add this thing, which is the structural decay materials. This is something that is not relevant. So you just put -1 and we don't have to think about it for this specific example. Now, think about an M-type def as one part that explains the rules of the universe. So we want to create new rules for the universe, which include essentially rainy materials of water and water generator. So first you do the super init that does the most annoying things to worry about. And then you only think about the new specific properties that you want to add. So first of all, we want to say immutable only propagates structural integrity, so it doesn't create nutrients. So you just set this to false, and from now on, immutable materials don't generate nutrients. Water is a gravity material, as I said. So you just say new gravity materials are the previous ones concatenated with water. That's it. Note that this is a JAX NumPy array so that you can use JAX arrays dynamically during the simulation. Now, you also want that water and water generators propagate air nutrients, even if they don't generate it. The reason is because of percolation. We are in a 2D environment, and if you have something on top and then there's no percolation, the air nutrients will not pass. So because of the limitations of being in a 2D environment, this is what I added this property. If you had a 3D simulation, you almost certainly don't need it. You can find some cooler ways of having materials percolate nutrients. But you just say add water and water generator to that. Okay, but these are some basic things. Now we need to add the rules for these materials. So this is what I want to do. Water checks if there's earth directly under it. If there is, it just gets absorbed and becomes air. And otherwise, it has a falling solid property, which is the one that you've seen on Earth. So last time, I just create everything set to 0 first, and just check if there's earth below. This is even easier than before. You just say down is earth. So if that's the case, then I want to say update both the target and myself, because remember, the target needs to change the nutrient values. So earth remains earth, but we want it to have more nutrients now. The value of nutrients is this, is like percentage to the maximum number of nutrients, and saying when water falls, add by 10% in this case. So I want to say to update the mask like this. And the type, we know that the neighbor type remains the same. We've already said that the earth remains earth in this case. But water will become air. Why air? Because it has already air nutrients, so it makes sense to just be converted to air. So you had some air nutrients, now it become air with those air nutrients. The target nutrients have to be increased. This thing is just literally sum, and make sure that it doesn't surpass the cap. And I do a conditional update for the state. Myself, I keep the same state as before, because now I will have the same air nutrients as before, which is the only state that I was using. And I keep the target update ID in case it becomes ever relevant. Now, I say I'm done if this is true. If it's not true, this is literally copy-pasting the Earth cell code. So this is literally copy-pasting it, the one you've seen before. That's it. We implemented water. Now, how does water get generated? Well, we have something which is very simple. It's a water generator. And it just says that water generator generates water below. It does it only if the type below is intangible, because we don't want water generator to destroy plants, essentially. That's the use case. And within a certain chance. It also preserves air nutrients because, again, percolation, we don't want to just lose air nutrients because we generated some water. If in our simulation, essentially water takes space of air. So, as you could guess, this is trivial. You just say, look down, and you say, the action happens only if there's an intangible material below and with a certain chance. The chance we chose here, in this case, is 2.5%. So 2.5% of the steps, you generate water below you if it's possible. And if you do, you just substitute the new target with water, essentially. And the rest becomes the same. There's some minor stuff. This is just saying this is the new number of exclusive operations that you would compute, which is air, earth, water, and water generator. Configuration, we can skip it. Doesn't matter. You just copy paste. Now, you want to create a new environment, and you can do it very simply by saying, create a multi-seed environment with many different seeds, so you will have a lot of different plants with a lot of diversity, in theory. And then you want to say that, so at the second top row, you add water generators everywhere. So on the first top row, you will have a sun that generates air nutrients. And on the second top row, you will get water. Did I execute this code? I did not. Okay. And this is it. Now you just essentially generate the new environment like this. And you will generate, this is like configurations which are default for all of the other things that you might care about, like what agents do we care? Do we want to have? Are they going to use sexual and asexual reproduction? In this case, both of them. Sex matters in sexual reproduction because we don't want selfing. And the agent model is a certain one, the mutation is a certain one, and this is all parameters for the environment that you can change however you want. This is for visualizing and just adding some metrics, and then you just execute this. Note that the step function is this ugly thing, but it's partial. So you do it once, you tell all of these static erg numbers, essentially, that are generated like this, and then you can just pass the step function and use it as having a 3 inputs, and that will just work. So this will take some time, but this is what will happen. You have an environment where rain falls from the sky, and it can accumulate. And the plants, if they don't figure out a way to make water fall down, they will die, because even if there's air nutrients, they cannot absorb them. You need to absorb them from air. So you need to give space to water to fall down. Otherwise, also, you will not get the capability of absorbing nutrients from the ground. Because there's no earth nutrients. So we could show it for longer, but we don't have too much time. So now it's 2:33, so feel like, completely free to leave. But I have an extra example of something fun that can happen, because once you have this done, you can play with it very quickly. You can just say, okay, now let's say that also roots can absorb earth nutrients. What would happen? And to do that is very, very trivial. I mean, for me, hopefully for even you from now on, which is you only have to change this thing. You go here and you say, before you were caring only that Earth is below you. Now instead say it's an array of possible types, which is absorbing types. So you define absorbing types of being Earth and agent truth. And now this is it. Now also roots will absorb water. Now, what do you think happens? Anybody wants to guess? Yes, somebody. Okay, so somebody said that the plants will go up, and that's half of what will happen. The other half is that this thing is not sustainable. But let me show you. So now roots absorb water. If you execute it, this is what will happen. First, everything is completely normal for a while. We need to wait for evolution to take its course. It happens relatively fast in these environments. Plants will start to realize, hey, I can just grow roots on top. And then this destroys the environment. This time they survived. The second time they do it, they all die. So this is an example. I mean, having biomes surviving is hard. It's not as trivial as you think, especially in small environments. Of course, if you got gigantic environments, extinctions events like this are not a problem. But I mean, you still have an extinction event, so you might want to avoid that as well. Yeah, so I mean, that's future work to figure out how not to make this get extinguished. But I guess you can always do meta evolution if you really want to make sure that it doesn't happen. And yeah, I'm done. Thank you. So with this, we are, how do I stop screen sharing? I already stopped sharing. Okay. Well, thanks everybody for attending. If you have any questions, you can say them now or afterwards.